few weeks ago I posted a video showing this device. It's a Rapid BCD keyboard encoder. It was sold as a small kit quite a number of years ago, and it's based around a simple PIC microcontroller. And the problem with it is the PIC was supplied in these kits totally unprogrammed, and so the owner of this sent me the PICs and one of the boards, and I just compiled the code that was in the instruction manual that came with the kit, programmed the controller, and it appeared to work. I didn't do any in-depth testing, sent it back to him, and since then you can see he's made this nice little board up to show the BCD output as each key is pressed. But unfortunately it's still not working properly, so if I press the keys you'll see why. If I press key 1, then we get 1, which is fine. If I press key 4, we get 4, which is fine. But if I press key 2, we still get a 1. If I press key 3, we get 3. If I press key 4, we get 4. Key 5 gives 4. Key 6 gives 6. So what appears to be happening is the first column values are all fine, and the last column values are all fine. But the middle column values are all showing column 1 values. So in other words, where it should be showing a 2, it's showing the value for column 1, which is a 1, in the same row. So if I press the 8 key, it will show 7, whereas 9 is fine. So it's scanning the rows, and it seems to be scanning the columns, but it looks like it's scanning column 2 as if though it's column 1. So he's sent this back to me, asked me to have a look at it, so we'll do that now. We'll try and sort out what's going on. So firstly, if we look at the row signals going into the PIC, then we can see that that is indeed fine for the first row. If we look at the second one, that's fine. So these lines just go high depending on which row the key is in that you're pressing. The way it knows which particular key is being pressed is it scans the columns. So I'll just check the other two rows. That one's fine, and that one's fine. So if we look at the column scan lines, we can see that one's switching fine, so is that one, and so is that one. So it does appear to be scanning the keyboard correctly, and yet it's coming up with the wrong values. Okay, so what we'll do is we'll go and have a look at the code that's in the PIC, which as I suspect where the problem is. And this is one of these interesting things that really my channel is all about. It's understanding the inner workings of devices like this. This keyboard kit was originally designed around the older version of this device, so it's a PIC 16F627, and that's what the firmware was written for. But this is the A version. If you're familiar with PICs, you'll know that as they developed, the individual pins became more and more complex, and so each pin on the PIC could be configured to do many different things: digital in-out, analog in-out, comparators, timers, that sort of thing. And the problem started arising as the pins became more complex, because it meant that you had to be increasingly careful how you wrote the code. Having scanned quickly through the code, I didn't really look at the code when I looked at this last time, I just compiled it and programmed the PIC. But looking through it, it's very badly written code, and I'll explain why in a minute. We'll go and have a look at it, and I'll explain why I think it's not working. We'll make some minor changes to it, and hopefully it will correct this issue, and we'll start getting the correct values when the keys are pressed. Okay, so looking at the code, the first thing to notice on this is that I did actually change it for the correct header file. So it was showing the 16F627. I changed that for the 16F627A. I did try it with the non-A version and it makes no difference. So the first thing we need to do is to have a quick look through this and see if we can figure out what's going on. I've checked for obvious typos and there aren't any. This is a lookup table for the BCD values. That's all fine. But firstly we need to look at these two lines, and on this particular device these port A pins need to be set to digital. Now in this case, because of the way they're being used, I don't think this is the actual fault, but we'll give it a go and see if that cures the problem. So all this is going to do, when the chip's initialized, it's going to make sure that these the port A pins are set to digital rather than comparator inputs, which is what they default to. As I say, I don't think this will fix the problem, but we'll give it a go. We'll build that and I'll program the chip and we'll go across, pop it back in the board. But I suspect it will do the same thing. Like I said, because of the way that these pins are being used, it shouldn't in theory make any difference. So we'll program the device. And we'll take it over, pop it back in the board and see if that fixes the problem. Okay, so we'll pop the device back in. As I say, I don't think this will fix it, but we'll try this first. Power it up and we'll see if we're getting the right code showing on the LEDs. So 1 is fine, 2 is wrong, 3 is okay. So as we can see, it's still not working. So next thing to do is look further into the code and see if we can figure out why it's still not working. Okay, so looking back at the code, I'm actually going to disable these two lines again just to simplify things. It will make the testing a bit more straightforward. But the first thing to note as we scan down through the code is these lines. And this is exceptionally bad coding on a PIC. If you try to perform or run a function that is a read modify write followed by another read modify write on the same port, on a PIC you can encounter issues simply because the two operations are done at effectively opposite ends, if you like, of the instruction cycle. And so because in a PIC the port pins, that's the values you see on the actual pin outputs, are not the same as the latch, then the latch value that you write when you perform a bit clear file, for example, that changes the value in the latch, but it doesn't change the pin value. If you then try and read the pin value in the next instruction, then you may well find the pin value has not yet been updated, and that's what you're doing here. You're changing what should be a pin value, but in essence you're changing the latch value. And then in the next instruction, because the first part of this instruction must be to read the port, so in other words, when you carry out a instruction like this, it reads the port, modifies a bit value and then writes the value back to the port. If the port value has not been updated from the last instruction, then you're reading in the wrong value into the following instruction, and these are all for the same port. So what could well be happening here is it's just simply not updating the values for the bits in this particular port in the way that the writer of the code intended. What you should really do here is read the port, make a change to the value you've read, either the entire value or just individual bits, and then write the entire value back to the port. That's the way you should really do this, otherwise you can end up with all sorts of weird intermittent faults. A quick workaround I'm going to use here, simply because I can't be bothered to change the entire code, is you can just put another instruction in between them. So in this case what we'll do is we'll just put an op between each of these. That will allow the latch value to make its way through to the pin value before the port is read again for the next actual instruction. We don't need to do the last one because the next instructions actually call to a delay routine, and we'll do this for each of these loops. Each column is scanned in a separate loop for some reason. So we'll do the same thing, and we'll separate these with knobs just to make sure that the port pin has a chance to update. Okay, so I suspect that may well have been part of the problem. However, one other thing I've noticed here is that obviously we have the issue in column 2, so this is the column 2 code, and there's a section here that calls the lookup table, which is this. And the lookup table is very straightforward. You've probably used this many times if you write much embedded code, and it's just adding a value in the W register to the program counter, and that causes the value that's returned to be the one that's looked up. So in other words, if you have a value, for example, of 2 in the W register at this point, then this instruction will cause a value of 2 to be added to PCL, so 0, 1, 2, and this is the value that will be returned in the W register. So it's a way of looking up values in the table. So if the value was 3, it will be the next one. If it was 4, it will be the next one, and so on. But as you can see, the way these are arranged, when we should be getting a 1, which is here, or rather when we should be getting a 2, we're getting a 1, and when we should be getting a 5, we're getting a 4, and when we should be getting a 9, we're getting a 7. So you can see these are all in kind of subsequent rows. So it does tend to indicate that what we're seeing here is an offset. There should be an offset value here, and if you count the difference, so 1, 2, 3, 4, 5, 6, 7, 8. So we've got a spacing here of 8, and so it looks like we've actually got an incorrect offset in the second loop. So if we look back down at the column 2 code, you can see that in the third column what they do is they flip the bits in the register that's holding the value that's been read, and that's a way for them to correct an offset. In the first column they just use raw values, which is fine, but in the second column there's no form of correction made, so this is looking still at the first column, which is obviously incorrect. So I think what we need to do is add a value of 8 here. I think the code is just wrong. I don't know how it ever actually worked. It doesn't appear to be correctly written. So what we'll do is we'll add 8. We'll do this before the mask instruction. We don't want, this is to make sure that we don't end up jumping off the end of the table. So we'll add an instruction here, and I want to add a literal to W. So add LW, and we'll do it in hex, a value of 8. So this will add 8 to the current value in W. So what we're doing here is we're looking or loading the value we've read from the port into the W register, which is what the 0 is for here. We're then adding a value of 8, and then we are masking that value to make sure we're not going to jump off the end of the table, and then we're calling the lookup table, and then we're continuing with the rest of the code. In theory, these steps, as far as I can see, should correct the issue we were having. So we'll try and rebuild that, make sure we haven't got any errors. That's fine. And now we'll try to reprogram the device. Okay. And I'll take it back over, we'll pop it back into the board and see if that's corrected the problem. Okay, so we'll pop the device back into the board, power it up, and see if we're getting the right values coming out of the device. So 1 is fine, 2 is fine, 3, 4, 5, 6, 7, 8, 9, not really sure what these values should be, 0, and then another value. Make sure it works in the other direction. 3, 2, 1. So that's now working fine. So the error is in the firmware. I still don't know how the firmware ever works, even in the non-A version. But as you can see, it's now working fine. And the point here really is that you need to know the inner workings of the devices that you're using. Otherwise, you can end up just going in circles for well, forever. And this, again, it's what my channel is all about. It's the fundamentals of doing things like this. It's a bit of fun, and I hope you found that interesting.